Hi, I wanted to do a short video to walk through a couple examples of some of the linear algebra concepts that we've been working on, but in relativity, so connecting back to where we'd been. And in this case, I'm going to define something called a 4-vector. That is oftentimes the way relativity concepts get communicated, at least in, well, maybe not in like usually undergraduate context, but sometimes in grad school context. Like when you get deeper into relativity, you'll see things written out in 4-vector notation. And this vector I'm going to write, sometimes you'll see it written like a standard vector, but more likely you're going to see it written with a little index down here. So this is an index, and this index can range from usually starting at 0 to 3. So there are 4 elements, which is why this is called a 4-vector. And this thing, sometimes you'll see it written out like this, where it has these 4 elements. Each element has a subscript, one of these indices. And really what this represents is the time and positions of this object or this event. This is really the space-time coordinates of some event. And we scale the time coordinate by c, kind of just like we were doing when we did our like space-time diagrams. This axis was ct and this was x, so that everything has spatial dimensions to it, but we're really talking about the time coordinate of whatever this event is. And this is really kind of putting it somewhere on one of these space-time diagrams. Of course, we usually draw them with just one spatial dimension because obviously drawing a 4-dimensional graph is very difficult. So you'll see things written out this way often. And we can also use this kind of notation to describe a space-time interval. So remember that this space-time interval is kind of defined as, we usually use s squared to talk about this space-time interval, and we might say it's something that looks like this, where we have the spatial coordinates squared minus the time coordinate squared, and this, depending on whether or not this is positive, 0, or negative, we sometimes describe this as, if s squared is greater than 0, that means the spatial displacement is larger in magnitude than the time coordinate. So we call this space-like, meaning that the separation between the origin and this, wherever this event is taking place, is more than the amount of distance that a light ray would be able to move in this amount of time t. So we can see this because a ray of, say, a spherical burst of light would travel a distance x squared plus y squared plus z squared is r squared. So I guess square root of this would be the total distance it would travel in some time t squared. It would move ct quantity squared. And so this is really just saying move this to the other, this ct to the other side, and then use that full thing to describe this space-time interval. And if s is greater than 0, we call that a space-like interval. If it is 0, then we get into the situation where x squared plus y squared plus z squared is exactly equal to ct quantity squared, and that would be light-like. That's exactly the way light would move. And then if the space-time interval here is less than 0, we call that time-like. And that's just saying whatever these two events are that are separated by this kind of distance in this space, you could send signals between each other, and they're close enough together that within this amount of time t, a ray of light could communicate within that. So basically, if you're in a time-like interval, you're somewhere within this cone. If you're in a space-like interval, you're outside of this this future cone there. And if you're along a space-time interval exactly equal to 0, you're light-like and you're exactly following one of these lines. Okay, so how do we actually define this space-time interval with these linear algebra concepts? We have to come up with a way of defining basically a dot product between these two vectors, because we want this length, which is kind of like the square root of x, or it's kind of like the magnitude, right, of this vector. Except in this case, we need to flip the sign of just the time-like term. We don't want to have x squared plus y squared plus z squared plus ct squared. And so we actually do something slightly different in the notation of this, and we define a new type of object that's very similar to a matrix. It's actually called a tensor, which is kind of a generalization of a matrix. And we're going to call this tensor the metric tensor. And I'm going to give it a name G, and it's going to have two subscripts here. I'll give it mu nu, because it's going to have some number of rows and some number of columns. In this case, it'll be a 4x4 matrix because we have a 4 vector here, and we're going to be multiplying it by this metric tensor. And since we need to flip just the sign of the CT term here, this matrix is going to be diagonal, but we're going to have a -1 here in that first index referring to that time coordinate, and then we'll have a bunch of zeros, and then the other diagonal elements will all be 1s. And the way this comes into play is we can actually just rewrite our inner product, our dot product. Sometimes the generalization of the dot product is called an inner product. And I'm going to put this, the indices for these vectors up top now. This is just kind of a convention that's used, that for inner products like this, the how do I want to say, the indices on the metric tensor go on the bottom, and the indices on the vectors go up top. And really this represents a summation over any index that gets repeated. So we're multiplying G, this metric tensor, just the elements that have that same new index times the elements here that would have that same new index. So this represents an entire matrix multiplication all in one line of algebra here, which is a little bit overwhelming at first when you first see this. So I'm going to rewrite this as what this would look like in the actual matrix multiplication version of this that we're more used to seeing, and then we'll try to just do one single example of seeing what this summation looks like, because there's a lot of math buried in this tiny expression. So I'm going to write out this first vector here. Remember, this is that space-time coordinate vector made up like this. And I write it now as a row because this is going to be multiplied by this 4x4 matrix that we know looks like this, or sometimes called a tensor, but I'm going to sometimes just refer to it as a matrix because that's how we're used to referring to this. And then this one will be a column. And again, just made up of x, ct, x, y, z coordinates. And now the reason why I ended up putting this as a row, so really this is kind of like the, in linear algebra, we would say that this is the transpose. So if x is the vectors, the column vector x, ct, x, y, z, then the transpose, sometimes written with a t superscript, is the same vector but now in a row format rather than a column format. So we transpose this vector, we have this matrix that just tells us something about the signs of the components, and then we have this column vector. And if we bring this back down, this would be equal to, well, this matrix is almost the identity matrix, but we have a minus sign here, so this just goes to, well, the row vector remains untouched because I'm not doing that matrix multiplication yet, and all this g does is flip the sign on the t, the ct term. So it's minus ct there, and we have x, y, z, and then we get to the point where we can do this matrix multiplication, and this column vector, remember we think of this column vector as weighting the columns of this, and each column here is only one element, so this just becomes minus ct quantity squared plus x squared plus y squared plus z squared, and we know that that is that space-time interval that we're used to seeing. And so this new way of writing this all allows us to, allows us to write this space-time interval equation in this kind of succinct form. To actually understand what's going on with these indices, we'd have to look at, let's say we want, so x mu, g mu, and then I'm gonna write out like 0 for nu. Well, this would be, and I'm just going to leave off the x mu part for now. How do I want to say this? Sorry, let me back off. And we're going to leave off the x mu altogether and just look at what is g mu 0 x 0. This means we're looking at the first column of the G matrix, and we're looking at all of the possible indices. So mu is now standing in for any index, so this is going to end up being a whole column vector, this thing, whatever this is. I'll call this y of mu. So we still have this mu, oh gosh, this mu down here. Let me bring this up so you can see it a bit better. This y mu will be a column vector with this index mu, but we're summing over just all the elements in the first column. The 0th column will be multiplied by the corresponding elements in this x vector. So here, g mu 0 would be the vector minus 1, 0, 0, 0. And we're going to, let's see here, make sure I'm saying all of this right. Multiply this by the elements ct, x, y, z. And this is just going to be a vector that has minus ct in it, and then the rest will be zeros. So this only just flips that sign because we only have this one element there that's doing anything here. And really, if we were this would just be the one of those columns that would be the result of multiplying this vector, or sorry, this matrix G mu nu times the vector x mu. And so if we did this entire matrix multiplication, we would get the first column would be the one we just did. The second column would be 0, x, y, z, or sorry, no, 0, x, 0, 0, and then 0, 0, y, 0, and 0, 0, 0, z. Because this is almost the identity matrix, and we then get these elements with just this one sign flip here, and then when we multiply it by the by this vector, we will end up just getting the thing that we're used to seeing, which is just this. And yeah, sorry, I guess since this is almost the identity matrix, actually the shape of this is wrong, and it would just return something that looks like minus ct x, y, z, like I said here. So sorry for that. This is a little bit confused. I get a little bit confused because I'm technically we shouldn't really think of it like this. We really need to kind of think of it in terms of summing over all of these indices. And so an easier way to look at this would be just to look at this kind of notationary thing, is to say, let me take some vector a equal like a mu, which mu, just let's for our sake just say that this it's just a two-dimensional vector, 0 and 1. So it has just two elements to it, and let's just call that, like, I guess a0, a1, and let's do b mu is b0 and b1. Then a mu, b mu would just be a summation over this everything where mu is the same. So this would be the sum of a, like I, b, I equals 0 to I equals 1. And so this is a0, b0 plus a1, b1. That's kind of what this notation means, and I really probably should have started there. And so when we have multiple indices, we imply a summation over nu here, and we have imply a summation over mu here. And so we end up with all of the indices going away, and we end up with just a scalar in the end. Whereas if we had something like this, where we had a summation over just one index, we would end up with something that would still have an index in it, so we would end up with a vector in that case. So yeah, sorry for getting a little bit messy there with that explanation. Okay, so I want to just briefly highlight that you can define other four vectors like the 4 velocity would be the derivative of that 4 position vector, the coordinate vector, with respect to the proper time. So remember, that's that proper time, which is the time as measured in the frame of the object that you're describing. And so I guess, let's see here. Then, of course, you might want to think about acceleration, and so you do the same thing and think about a 4 acceleration as a derivative of the 4 velocity with respect, again, to the proper time. And then lastly, the last thing you might want to do is define a 4 momentum, which is gamma mc, or yeah, comma m gamma like Vx m gamma Vy m gamma Vz, which sometimes gets just shorthanded to gamma MC gamma M V vector, like where this V vector is the normal vector that we're talking about with the components x, y, and z. So sometimes we'll see that as our definition of form momentum. Okay, so I'm not going to go into too much of this, but you can do all of the kind of kinematics and describing of motion of objects all the way that we did in like a Newtonian sense, with basically all of physics 1 and everything that you've done up till now. You can do with these four vectors and define forces and energies and things like that, to do any sort of kinematics. But I'd rather focus on something we have seen with relativity and talk about the Lorentz transformations and how those connect to this linear algebra. And so I just want to highlight how you can rewrite the Lorentz transformations in terms of these four vectors and matrix multiplications. And if we do that, I can write out a matrix which is made up of things that should look relatively familiar. Yeah, make sure I'm doing all this right. So we get something that's, again, almost a diagonal matrix, but here we have some off-diagonal terms that relate the unprimed coordinates to the primed coordinates. And so this is like, I'll say x mu, and then this would be L mu nu, because it's two-dimensional. It has two indices here, and then you have x nu, and again I've got upper and lower indices. Again, this is really just kind of convention, like how do you write these things? And here, since we're summing over nu, we're going to end up with a vector still, and since mu is down here, mu is up in the lower index here as well. So this L, this is our Lorentz transformation written out as a matrix transformation. And of course we could write the inverse transformation, where we go get the primed coordinates from the unprimed coordinates. And our inverse of this Lorentz transformation, all we have to do is swap the primed and unprimed coordinates and swap the velocity, meaning beta, sign. And so we just have now a minus gamma beta minus gamma beta 1 0 0 0 0 0 0 0 0 0 1 0 0 1, and all that is times, sorry, oh, that should be CT x y z. Now and of course this is our inverse transformation. Again, I'll give it some mu nu indices. This would be x prime mu times x nu unprimed, for that kind of compact summation notation. But let's actually just plug in, for example, just look at the x0. So let's say mu is 0. We'll have L0 nu x nu, and look at just that one line of this. And so in this case, x0 is CT, and L0 nu represents just the first row and the entire first column here, and we're going to be multiplying that by this element by element. So we'll get gamma ct prime plus gamma beta x prime, and then that would be, the rest of these are going to be zeros, so we're not going to pick up any y or z primes. And so we could then rewrite this equation, just say divide by c and factor out this gamma from both of these terms to get gamma t prime plus beta over c x prime. And that is exactly the same transformation that we have had before. Of course, you could write this, the way I think I probably wrote this before was rewrite beta as v over c to get vx prime over c squared. And that is the same transformation we're used to. And so that's one way where we can use this matrix multiplication to give us these Lorentz transformations, and this would work for any Lorentz transformation. So here, this is again assuming that the only relative motion is with a constant speed v along just the x-axis. And so that's why the kind of y and z pieces of this matrix are just purely diagonal with them. Like if you looked at the x 3 version of this, would be just z, and that would be just z prime. If you did this whole version where now mu was 3, you would just get this relationship, which is what we expected. Okay, so that's showing the Lorentz transformations here. The last thing I wanted to highlight is actually more related to the kind of eigenvectors and stuff that we've been doing more recently, and connecting it to these space-time diagrams that we spent a lot of time looking at when we were doing relativity. And recall that in these space-time diagrams, a Lorentz transformation was just a stretching and squeezing of any world line along these light lines, which these light lines are 1, 1 and minus 1, 1 in these scaled coordinates that we use. That makes these at 45 degrees. So now we can realize what this means fundamentally. These vectors are the eigenvectors of this Lorentz transformation, because if we tried to scale with this Lorentz transformation a light line, we're going to get that same light line out. Like if we take this like a object, or like think of it this way. If you have a ray of light moving in this unprimed coordinate system, you're going to see it move along this light line. And if someone was moving in another coordinate system at constant relative velocity to you and saw that as being emitted from their x prime equals 0 origin at t prime equals 0, when those two frames briefly overlap, they would also see this move along a light line, because everyone sees light move at the speed of light. And so you end up getting where both people will agree, no matter which frame you're looking in. So this Lorentz transformation still has if you multiply it by this vector, you will end up getting the same vector out scaled by some constant multiple. So like maybe it points a different distance, but it's still pointing along that light line. And this is our definition of what a eigenvector is. I want to briefly figure out like what are these eigenvalues and what's the meaning behind these eigenvalues. And so to do that, I'm gonna let's simplify L to just be a 2 by 2 matrix, so looking in one spatial dimension and one time dimension. And let's say I rewrite it like this. I'm gonna, I guess, in this version of this, I could rewrite my Lorentz transformation in a matrix equation like this. So here, x, ct, like that. And if I wanted to, let me define a matrix made up of these eigenvectors like we've done before when we are trying to rewrite this matrix equation in the eigenbasis so that we can easily find the eigenvalues. One way we have done that in the past is, say, if we wanted to diagonalize this matrix, so here's a diagonal matrix, I could take this matrix, which is the matrix that I can use to diagonalize it, meaning if I write this matrix L in the eigenbasis, it will be diagonal with the elements of the matrix being the eigenvalues, and that's this matrix. So D should be just lambda 1, 0, 0, lambda 2. And I do that by multiplying by this special matrix on one side and its inverse on the other side. And that will transform me into this specific basis that allows me to see this diagonal property of the matrix. And so I could instead say, well, let me just multiply by the inverse of these matrix in the opposite way on this side and say, well, this would give me this. If this is true, then this has to be true, right? So I can do the same thing and convert from this diagonal matrix to L using the same set of matrices. And I know what A is and what I could find. Let's say A inverse would be, well, the determinant of this would be 1 minus negative 1, so it's 1 over 2 times the matrix 1, I guess positive 1 minus 1, 1 is my inverse matrix. So then I can rewrite L, which I know, as A, which is 1 minus 1, 1, 1, times this matrix, which I know should be made up of the eigenvalues, times that inverse, which is going to be 1, 1, minus 1, 1, and I'll put a 1/2 just out front because it's a constant. I can move it wherever I want. Now, I'm going to save some algebra here and let you do this, but if you do that, you should end up with a matrix L, which should be equal to, in terms of the eigenvectors, lambda 1 plus lambda 2 over 2, lambda 1 minus lambda 2 over 2, lambda 1 minus lambda 2 over 2, and lambda 1 plus lambda 2 over 2. Which I'm going to factor out this lambda 1 plus lambda 2 over 2, which means that this becomes 1 on these diagonal elements. And then the off-diagonal elements will be lambda 1 minus lambda 2 over lambda 1 plus lambda 2 for both of them. Like that. Now, why do this? Because we know this is equal to that, because this is just L. So if I do this, I can factor out a gamma from this term, and so L can be written as gamma times 1 minus beta 1 is equal to this. And so since these are 1s, and this is the thing out front, that means gamma has to be equal to lambda 1 plus lambda 2 over 2. That's actually an interesting property. Gamma, which we know, that's that thing that's 1 over the square root of 1 minus beta squared, is actually the average of the two eigenvalues of this Lorentz transformation matrix. So we now have some connection to what these eigenvalues are. And if I look at these other off-axis elements, well, if I now bring this back in, I can say gamma beta, so gamma here times beta, make sure I'm saying all this right, is going to be equal to, there's a minus sign here, so I'm going to swap the order of these in the numerator in there, will be gamma 2 minus gamma 1 over lambda 1 plus lambda 2. So I could solve for beta in this equation. So I got lambda 2 minus lambda 1 over lambda 1 plus lambda 2 times, I guess, 1 over gamma. So I'll say 2 divided by lambda 1 plus lambda 2, which is now 2 lambda 2 minus lambda 1 over lambda 1 plus lambda 2 quantity squared. So this one, we don't get as much physical insight, but there is a relationship between these eigenvalues and beta and these eigenvalues and gamma. And so, of course, this again now represents a system of equations, two unknowns and two equations, so we could solve, I'm not going to do it because it's a lot of gross algebra, but we could say lambda 1 equals something as a function of, I'll say function of gamma and beta, and lambda 2 is some other function of gamma and beta, and we could figure out that relationship, but I don't want to do that. Anyway, there is the main important thing is that we can use this linear algebra to describe these transformations, and that we can even think of them in terms of these eigenvalues and eigenvectors, and that the eigenvectors are these light lines that were so important when we were talking about space-time diagrams. So that is just a short glimpse of a couple ways that the linear algebra we've been talking about is related to the relativity we did earlier in the semester. Okay, so that's it for this. We are going to be talking about geometric transformations and things like rotations and how those are related to matrices on Monday. Okay, bye.